Traces of a 2,000-year-old past. A Roman villa on the future site of the LHC. Archaeologists are at work. For them, unearthing these objects and accurately detecting the plans of this house is a little like traveling in time. It's attempting to understand how men lived in those days, what they were thinking. Man's instinctive curiosity about the past manifests itself today in a new type of archaeology. It uses a giant machine whose aim is to go back in time to understand the origins of the universe 15 billion years ago. What do we see in this dim, distant past? First, particles without mass, in the heat and chaos of the first moments of the universe. Later, the temperature drops, and the hidden harmony of the universe can unfold in its infinite form. It envelops everything, and allows the particles to find their identity, determining their nature, and above all, giving them a mass. Each one, according to its nature, will therefore acquire its own energy, a different mass. Let's freeze the frame at the moment when a blue particle is in proximity to the element which was responsible for this metamorphosis. The first challenge for the LHC is to identify it. Today, physicists think that in parallel with the birth of ordinary matter, a perfectly symmetrical world was born in our universe. With each particle observed today will be associated a similar partner, but with a much higher mass, called a supersymmetrical particle. Another challenge for the LHC: identify this partner. Another scenario, perfectly compatible with the first, captures the imagination of physicists. They think that in the beginning, an equal amount of matter and antimatter appeared. Each particle, therefore, would have been born with a twin sister. When they met, they mutually annihilated one another. Rarely, one particle has appeared solitary. It has not disappeared. Why? Another major question for the LHC. To transform these hypotheses into certainty, a first step was taken. In the 1980s, a 27-kilometer circular tunnel was dug out of the rock 100 meters down. And in this tunnel, the LHC, a particle accelerator. It's situated near Geneva, at the foot of the Jura Mountains. The LHC accelerates electrons and positons. Unfortunately, the more electrons are accelerated, the more they develop their own braking system, emitting light. To go beyond the limitations of the LHC, a new, much more powerful machine had to be designed. Instead of using electrons and positons, the LHC will accelerate other particles, protons, which are much heavier. The conditions will produce explosions of matter similar to those which happened at the dawn of creation. Compared to the LHC, the LHC is totally revolutionary. It accelerates protons which are 2,000 times heavier than electrons at a speed close to that of the speed of light. At this speed, the protons acquire a much larger effective mass. Under these conditions, the centrifugal force would tend to drag the flux of protons outside its trajectory. To avoid this, extremely powerful magnets have been installed all along their path, forcing them to remain precisely at the center of the tube in which they're contained. In reality, two proton fluxes circulate in opposite directions in the accelerator. They only meet in the physics detectors. An innovative design allows the two opposite fluxes of protons to move in the same magnetic field. These superconducting magnets use special materials which transmit electric energy with no loss through heat dissipation. A continuous flux of superfluid liquid helium maintains the temperature at -271 degrees Celsius. Thanks to the cold superconducting materials combination, the consumption of electricity by the LHC will be no greater than that of the LEP. At a certain moment, the protons pass through acceleration cavities, and this gives them a small kick of 6 million volts per meter, propelling them forward at a speed approaching 300,000 kilometers per second.